So let's put 4 particles in a container. Here's our container. Here's one particle, black particle. Let's have a pink one. Let's have a green and a blue. Now, let's say that there's 6 quanta of energy to disperse. How many microstates is possible? Well, gosh, let's say that we started number 1 with all 6, 3, 4, 5, 6. Then let's say we started 1, we could do 1 quanta here and 5 here. And then we could do 1 and 3 here and then 1 and then 1. So think of, I mean, that just gets to be huge and almost unbearable to think about. So if we were to look at this and go, okay, so if we've got 4 particles, here are all of the different ways that we can arrange that. There's 84 different ways, more than you're ever going to have to draw or think about. But we could have 3 particles with no energy, and 1 with 6. And there's 4 different ways we could do that, right? Which is what this is telling us. The black one could have all quanta of energy. That would be 1. The pink one could have all 6. The blue one could have all 6. And the green one could have all 6. So there's 4 different options there. We could have, again, 4 options where 3 different colors had 1 and 1 had 3. So that would 1, 2, 3, 4, 5, 6. Now we can see all of the different arrangements here. And really the point is, when we were looking at just this, where we had 4 particles and only 2 quanta of energy, think of the mess, and that only had 10 microstates. We have 4 quanta with 6, and notice that increase, that's huge. Entropy can quickly increase, which is logarithmic, and we can see that when we raise something to that power, how it can exponentially just rise. So again, just to recap, there's 84 microstates possible in that situation, and we were really looking at the difference was all we did was go from 2 quanta to 6. We had 4 particles in that first, and we had 4 particles in the second example, but just from going from 2 to 6 made us go from 10 to 84 different microstates. So as that number of particles or quanta increases, that microstates grows rapidly. So a couple factors that influence entropy is the phase of the substance. So if we think about solids, liquids, and gases, we have very organized particles that are in a nice, even, neat arrangement for solids. They become less organized as a liquid and even really, really unorganized as a gas. It's very chaotic as a gas. So entropy increases as we move from a solid to a liquid to a gas. And also the temperature of the substance affects it, because the higher the temperature, the faster those particles are moving and the more chaotic the system is. So as temperature increases, so does entropy. So temperature, we know that is directly proportional to kinetic energy. Higher temps, they have more freedom to move around. So here's an example of looking from a solid to a liquid to a gas. We can see that there is less organization, and delta S increases as we go from solid to a liquid to a gas. Here's a good one where we look at entropy and temperature. So here we have a solid where we're at 0 degrees until we hit melting. So this is from here to here, we're melting. So we're going from a solid to a liquid. But so temperature does not rise here. However, notice that entropy still increases. going from that solid to a liquid state, that disorganization becomes greater, even though temperature is not. So again, doesn't mean that we can't increase entropy, even though temperature is staying the same here. Entropy is still increasing during that phase change. And then once we're all a liquid, we go from, this is all liquid, this was solid, this is liquid. Let's say this is water. We're rising from 0 degrees to 100 degrees, all in liquid, and temperature is increasing, entropy is increasing. Then we hit boiling. So now we're going from a liquid to a gas. Notice the entropy is increasing in that phase change. Once we hit, let's say, 100 degrees Celsius, and we are in gas phase, notice entropy continues to increase as temperature increases. When we look quantitatively at the entropy values of liquid water versus gas, so we've said that entropy increases, right? Energy dispersal increases as we go from a solid to a liquid to a gas. But if we look, again, numerically, we look at liquid water, entropy is 69.95, so about 70. And the entropy for water in gas phase is significantly higher at almost 190. Again, this is joules per Kelvin mole of the units the entropy is expressed in. Also, as the size of the container increases, the number of microstates accessible to the system increases. So the entropy of the system increases. If we think about the number of microstates available in this container versus if they have both accessible, how this has increased the entropy of the system. Ludwig Boltzmann said that as the number of microstates increases, so does the entropy of the system. So write this equation down and know it. Entropy, the entropy of a system is equal to Boltzmann's constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin, times the natural log. Natural log is ln on your calculator key. Natural log of W. And W stands for the number of microstates available. So this relationship allows us to predict how many microstates are possible if we know the standard entropy value, like you were given in the last slide, if we know the standard entropy value of liquid water versus gas water in gaseous state. So we can find that because we would know Boltzmann's constant, and then we would do the opposite of the natural log. So the natural log is based off of Euler's number. So that's its base. This is different than using log. Log is base 10. We're not using that. We're using the natural log, ln. And what's nice is we know all of these standard entropy values. They're all in the back of our book or the back of our text or the resource that I will either email you, but you will be provided with it. And this has all of the thermodynamic properties. We used it last chapter when we found the heat of formation. When we were calculating enthalpy, we'll use it this chapter when we are looking up standard entropy values, and we will use it later in our chapter when we're looking up Gibbs's free energy. All right, so let's look at the change in entropy for a system going from a condition with 5 accessible microstates to 30 accessible microstates. So we're going to plug it into our entropy equation where we use Boltzmann's constant, and then we find the natural log of, remember capital W stands for our number of microstates, our initial, which was 5. So we have final over initial. Final was 30. So let's write this out. Our delta S is equal to Boltzmann's constant, which is 1.381 times 10 to the negative 23rd joules per Kelvin. And then we're going to do times the natural log of 30 over 5. So let's do some calculator work here. First, I'm going to do our natural log, ln, of 30 divided by 5. I get 1.79175. But I'm just going to hit times our Boltzmann's constant. Times our 1.381 times 10 to the negative, times 1.381 times 10 to the negative 23rd. And I got 2.47, so delta S, 2.47. How many should we'll go to 3 decimal spots since that's where it bolts with. 474 times 10 to the negative 23rd. And remember that that's in joules per Kelvin. And this is a positive number. So entropy has increased, right? And that makes sense. If we went from 5 microstates to 30, we are increasing our state of disorder. And we can double check this, and if we think about it, what if I went from 30 microstates to 5? So I'm decreasing. Let's see what that does to delta S. If I plugged it in and said 1.381 times 10 to the negative 23rd joules per Kelvin times the natural log of, what if I did 5 over 30? Let's try that. The natural log of 5 divided by 30, which is negative 1.79, times 1.381 times 10 to the negative 23rd. Notice I had a negative 2.47, so that would be my entropy is decreasing. So that would be becoming more organized as opposed to going from 5 to 30, it's becoming less organized or in more of a greater state of disorder. Let's look at a sample problem. So with 2 dice, each numbered 1 through 6, there are 2 possible ways to roll a 3. A 1 and a 2, this is one way, where one dice says a 1 and dice number 2 says 2. And then here's the second way, where the first dice you roll a 2 and the second dice you roll a 1. So how many possible ways are there to roll a 6? All right, so let's say we have 2 dice. One way would be to do a 1 and a 5. We could also roll, I've got 2, a 5 and a 1. Third option, so that's with dice 1. I can do a 2 and a 4. I can do the opposite of that. So option number 4. One dice I can do 4 and a 2. And 1, 2, 3, 4. And then I can do a 3 and a 3. I think that's our only options. We did 1 and 5, 5 and 1, 2 and 4, 4 and 2, and then 3 and 3. Yeah, so we have 5 options here to roll a 6. So let's figure out the entropy associated with the outcome of 6. So we're going to use our S is equal to Boltzmann's constant times the natural log of W, which is our microstates. So 1.381 times 10 to the negative 23rd joules per Kelvin times the natural log of 6. And let's put that into our calculator here. The natural log of 6 times 1.381 times 10 to the negative 23rd. We should get 2.474 times 10 to the negative 23rd joules per Kelvin. Oh, wait a second. I was thinking that this number looked very similar to what we just found back here. And you know what I did? Why did I do the natural log of 6? I was thinking that we were rolling in number 6. See, this is a good thing that we go back and check answers because I made a goof. We want to use right here for the natural log of 5. Goodness. All right. So let's redo this and do the natural log of 5 since that's how many microstates we are. We're not doing the natural log of 6. Come on. All right. The natural log of 5 times 1.381 times 10 to the negative 23rd. Oh shoot, what did I do? The negative 23rd, 1.381. There we go. I should get not this answer. I should get 2.22 times 10 to the negative 23rd joules per Kelvin. Okay, let's make sure I did this right. We had 5 microstates, yes, that add up to 6, so we do the natural log of 5 times Boltzmann's constant to get 2.22 times 10 to the negative 23rd. All right, this next slide tells us that an increase in molecular complexity generally leads to an increase in entropy. And if we think about this and we look at methane, methane is CH4. And if we think about all of the different possible microstates or arrangements that one molecule of carbon with one molecule of methane, which is 1 carbon with 4 hydrogens around it. It has an entropy value of 186.3. Then, if we look at ethane, which is 2 carbons surrounded by hydrogens. And remember, bonds can bend, bonds can move, and twist and turn. So now we're adding a little bit more complexity to it. Notice that its entropy is 229. So it has greater entropy value. So more arrangements, right? So the larger the molecule gets, usually there's an increase in S. And then here we see this with propane. Now we have 3 carbons with hydrogens all surrounding it. Again, think of all of the different microstates and different arrangements that propane can have. And it has an entropy value of 270.3. So as the molecule gets bigger, then entropy generally increases. We can also look at the entropies of ionic solids, and it depends on their Coulombic attractions. And what does that mean? So let's say that we have magnesium oxide. We have magnesium with a +2 charge, and we have oxygen, which when it becomes an ion, oxide. And we can see this +2 -2, this is going to give us a tighter bond. When we have that greater attraction to one another, they're actually in a more like fixed position. So they have magnesium oxide has a lower entropy value because that greater attraction between the higher charges keeps them from moving. They're in a more fixed state. They just aren't able to have that more mobility. And then we have our Na, our sodium, with a +1, and fluorine with a -1. It's less of a tight bond, less tight. And notice that it has a value of 51.5. So we can see that these are more movable, more flexible bond. And the tighter the bond, the greater that charge is, the more fixed position it is, and it keeps them from moving as much, so they have less entropy. So as we wrap up this section, I want you to think, what is the first law of thermodynamics? What is the second law of thermodynamics? These are questions that you're going to be asked on the test. So take a second and pause the video and see what you can write down about what you know about these two laws. I hope you wrote something like this. So our first law of thermodynamics, energy cannot be created or destroyed. It must be conserved. It may be transformed from one form to another, but it is always conserved. And we have the total system of the universe. We know that that is equal to the amount of heat plus the amount of work. And that's a lowercase w. And the second law of thermodynamics, for a process to be spontaneous, the sum of the entropies of the system and the surroundings must increase. So entropy of the universe increases. So we know that if it is greater than 0, then we have a spontaneous reaction. If the entropy of the universe is less than 0, it is non-spontaneous. Spontaneous in the opposite direction, but in the forward direction, non-spontaneous. And if the delta S of the universe is equal to 0, then it's reversible, and that our system is at equilibrium. And we're going to be spending the next couple chapters talking about equilibrium. Remember, the system is the part of the universe that is of specific interest, and the surroundings is the rest of the universe that's outside of the system. That second law of thermodynamics is very important. If we look at our delta S, or entropy of the universe, is equal to the entropy of the system plus the entropy of the surroundings. So we have our system and our surroundings. If the delta S of the universe is greater than 0, it's a spontaneous process. If the delta S is less than 0, so a negative, it is non-spontaneous. Positive is becoming more disordered. Negative means becoming more orderly. If the delta S of the universe is 0, the process is at equilibrium. Let's look at a couple of questions to wrap up this lecture. Which reaction produces an increase in the entropy of the system? So remember, when we're looking at entropy of a system, we know that gases have the highest entropy of all states of matter. Okay, so let's look at this. We have N2 plus 3H2 to give me 2NH3. They're all in the gas state. But if we look here, I have 1 mole of gas plus 3 moles of gas. I have 4 moles of gas combining to create 2 moles of gas. So this is becoming more organized. All right, so our delta S is going to be negative, right? That is unfavorable. All right, let's look at this. I'm going from liquid water to solid water. So a liquid to a solid is becoming more organized. That is negative. That is unfavorable. Here, I've got gas, gas, gas. All right, so I've got 1 mole of gas plus 1 mole of gas. So I've got 2 moles of gas. And over here, I have 2 moles of gas. So 2 is equal to 2, and they're all in the same state. So I'm going to say that that entropy is equal to 0. So no change there. So it's not an increase. We're going to say no change. Here I've got solid CO2 going into gas CO2. Oh, that's good. Solid to a gas. That definitely is a positive delta S. That is an increase in entropy. All right, so this looks good so far. Let's just check this one. Here I've got silver ions in aqueous solution plus chloride ions in aqueous solution going to silver chloride as a solid. So here I have aqueous, so liquid to solid. That's definitely becoming more organized. That's negative. So we have our answer right here, our solid CO2 going to gas CO2. Let's look at another. Let's look at this one. Delta S is positive for which reaction? Well, we've got a liquid and a gas combining to form a solid. So that's becoming, our delta S is negative. It's becoming more organized. Let's look at this one. We've got gas, gas, gas. All right, well, let's look at quantity of gas. I've got 2 moles of gas plus 1 mole of gas. So 3 moles of gas combining to form 2 moles of gas. Nope, that's becoming more organized. This one, again, I've got 2 gases. So I've got 2 moles of gas combining to form 1 mole of gas. No, that's also negative, becoming more organized. Here I have a gas going to a solid. That's definitely becoming more organized. And then here I have a solid decomposing into 2 aqueous ion solution here. So that is definitely becoming more disorganized. All right, we have 2 more. Delta S is negative for this reaction. Let's check it out. So we have gas, gas, gas. All right, so now let's look at quantity. 2 moles plus 1 mole, so 3 moles going down to 2. Oh, yeah, our delta S would be negative for that. Okay, well, let's keep looking and see if there were any other options or if this is our answer. All right, this one we have a solid, no, and solid's going to drop out here. So let's look at our gas compared to gas. 1 mole to 2. No, that's becoming positive. That's positive. Here I've got solid to a gas. Yep, that's a positive. Here I've got solid to aqueous. So in solution, that's a positive, just like our last one. And here we have a liquid to gas. That's a positive also. So yeah, we are. Number 1. And let's go to the last one. So which of the following linear chain alcohols is likely to have the highest standard entropy in a liquid state? Which one would you choose? Well, like you, I would choose this last one because it is the largest molecule, has the most number of bonds, it is the heaviest molecule, and all these bonds are able to move and have much more disorder than my